Welcome to the 16th annual William E. Larson and Raymond Alvarez lecture on emerging issues in soil and water. My name is Satish Gupta. I'm a Raymond Alvarez Professor of Emerging Issues in Soil and Water in the Department of Soil, Water and Climate. After having that snowstorm over 2 weeks ago, I didn't think we would ever recover. So it's a great day outside, and I do appreciate you guys all coming inside here to listen to our lecture proceedings. Before we go on to the program, I'd like to take a few minutes and introduce some of our guests who have come from far away places like Oklahoma, Colorado, and Washington or Baltimore. We have both here Bill and Ray's families. When I call your name, please just wave your hand so that the audience knows who you are. We have Bill's eldest son, Dr. Larry Larson. Larry is with the Mayo Clinic at Mankato. Really appreciate Larry. I know it's been very hard on your schedule, but we do appreciate your coming in for the lecture over here. And we also have Bill's other son, I think, on Steve Larson and Bill's granddaughter, Alicia Lee. I think on the live, they were going to view the proceeding live on the web. And then we have Ray's daughter, Joan Alvarez. Joan is from Edmond, Oklahoma. Ray's other daughter, Mary Alvarez. Mary is from Denver, Colorado. Joan was a owner at one time dealing with business on the oil exploration, and Mary is vice president for CenturyLink. We also have a Dr. Stephen Maris here, Ray's son. He's a research engineer at MIT in Baltimore. And we have Ray's grandson, Mary's son, Anthony Alvarez. Anthony is also from Colorado, which is my favorite state because my son lives there. Anthony is a junior in high school, and he has been coming here at least for 7 or 8 years. And I remember one time he promising me that he is going to follow his grandpa's footsteps and become a soil scientist. Right, Anthony? All right. I think we also have Colleen Adamo, which is she's Ray's other daughter in California. She works for Hewlett Packard, if I remember correctly. And we have Kathleen Alvarez in Washington State. They are watching the proceedings live. The other member of Ray's family at the event are Ray's sister Camilla Lex, Ray's other sister Lorraine McManaman, and Ray's nephew Joe McManaman. He's probably, okay, he didn't make it, looks like. Oh, he's there? Okay. Oh yeah, I didn't. They just flash, fast. We have Ray's sister and brother-in-law Patty and Dwayne Strawley. And then we have their daughter-in-law Jan Strawley. Is Jan here? Okay. And we have Ray's niece Adele and husband Mike Jacoby. They're from Hector, Minnesota, so they didn't have to travel that far. We're glad to have you. Well, thank you very much for taking time out of your schedule and to be part of the event. We really appreciate Ray's family setting up the Raymond Alvarez Endowed Professorship, as well as supporting Ray Alvarez Graduate Student Fund, and also contributing to this lecture series. Let's give a big hand to both Ray and Bill's family. This is the counterpart series to Keena's lecture that we have in the fall. Mark Seeley used to organize that. He retired last year, this year I think. And we started this series mainly to highlight the expertise in our department in the area of soil and water, as well as to recognize Bill Larson and Ray Alvarez's contribution to our discipline. The lecture series also provides a forum to explore emerging issues in the broad area of agriculture research with specific emphasis on the environment. As I mentioned, this is the 16th year we have had a wonderful set of speakers. And our first featured speaker was Dr. Ratan Lal. From the Ohio State University, the committee selected him because of his background on soil tillage and the expertise which was very similar to Bill and Ray's expertise. And some of us have worked in the area of soil tillage research. This October, Dr. Ratan Lal will be the featured speaker at the Gustavus Adolphus College Nobel Conference in St. Peter. The theme of that conference is Living Soil, a Universe Underfoot, similar to what we are doing here. I hope some of you will take time to attend the conference. I'm also talking to Ratan Lal and see if we can have a seminar from him in our department before he goes to St. Peter for the conference. The theme of this year's conference event or lecture event is Nitrogen Cycle and Agricultural Sustainability. Today's program is a collective effort of many people, including the lecture committee, office staff, and graduate students. The committee consists of Paul Capel. Paul is with the USGS, and then we have Fabian Fernandez in our department, Jane Johnson with the USDA ARS Morris, Helene Murray in agronomy department, Gary Sand in bioproducts and biosystems, Mark Seeley in our department, Jeff Strock at Southwest Research and Outreach Center at Lambert, and Bruce Wilson of bioproducts and biosystems. This will be the last year I'll be organizing this event, lecture event. I'm planning to retire early next year. For some of you who have been working in the Minnesota River and Lake Pepin issues, please don't open the champagne bottle yet. Okay, I plan to be around and active in that research and still try to address some of the issues that might come up along the way. At this time, I want to thank the committee as well as Carrie Jerko and Stacy Nordstrom, our office staff, for all their help putting together this year's event. My special thanks to Rod Ventria. Is Rod wrong? Yeah. Yeah, Rod is in the back. He suggested Dr. Davidson's name for the lecture this year. I also want to thank Jared Speckman, our graduate student president over here, for organizing the get-together of graduate student with Dr. Davidson this morning. The sponsors for this program, this year's program, are the North Central Sustainable Agriculture Research and Education Program, Minnesota Association of Professional Soil Scientists, Spectrum Research. Dr. Jim Block is the president of that, and then Irene Leonard True Endowment. My sincere thanks to all the sponsors for their continued support of this generous and continued support of our lecture series. Now I request Dr. Carl Rosen to come over here and give a few updates about our department.
Thanks so much, Satish. Here we go. All right. Thank you very much, Satish, and welcome to the 16th Annual Larson Almaris Lecture. Satish kind of dropped the retirement bombshell on me a few weeks ago, and I knew it was going to come eventually, but we never quite prepared for when it actually happens. And Satish actually told me this lecture series is not about him, but I have to say a few words about Satish. He only gave me 3 minutes, but it's going to maybe take an extra minute or two, Satish, so bear with me on that. We very likely would not be here if it weren't for you, Satish. So let me just give you a little background. Satish started here in 1972 as a postdoctoral fellow with Bill Larson. So there's the first connection. Bill was the ARS research leader at the time. And then in 1977, Satish officially joined the ARS unit, Soil and Water Management Unit, in 1977. And then in 1985, he joined the department. And that was the same year that Ray Almaris came back to Minnesota to work in the department as well. So there's a great connection there. And since that time, Satish has been responsible for soil physics teaching and graduate research programs. He's done a fabulous job with that. And you know, Satish, I'm not going to go over all your accomplishments now because there's a lot. And we'll save that for your retirement party, but suffice it to say that Satish is a distinguished soil scientist recognized for his pioneering work in compaction, tillage, water quality, and most recently bank erosion, Lake In 2013, he was selected as the first recipient of the Raymond Almaris Professorship in Emerging Issues in Soil and Water. And this endowment, as Satish mentioned, was established through a very generous donation by the Almaris family. It's intended to attract and retain outstanding faculty, particularly in the areas of soil physics and hydrology. And it was Satish's idea to start this seminar series, and it was in honor of Bill Larson and Ray Almaris, his mentors. This was started some 16 years ago. And through this series, I've especially enjoyed getting to know the Almaris family and their extended family. It's been really great. And I'm most appreciative of their support and generosity over these years. So I can't say for sure what the plan is for next year, but I can say that we are committed to continuing this series for many years to come, and we hope to see many of you next year for that. Okay, so before I close, I usually give a few departmental updates. I'm going to be really brief on this, but it has been a busy year. We've hired 3 new faculty. Yusun Miao, he's in the audience there. Just raise your hand, Yusun. He's going to teach and conduct research in precision agriculture. Melissa Wilson in the back there, she's our new extension specialist in manure management. Very timely topic for today. And we also hired Lindsay Peace, who's from Ohio State. She'll assume a position in nutrient and water management up at the Northwest Research and Outreach Center in Princeton starting in August. So we're looking forward to seeing her then. We've recently completed 2 additional searches for extension position. One is the irrigation and water quality specialist, and that position will start in July. And then we also completed a search for a soil health specialist, and we might hear a little bit about that in a few minutes from John Jaski. As many of you know, Mark Seeley retired this past February, and even though he leaves big shoes to fill, we can give approval to start a search for his replacement, and our goal is to hopefully have somebody hired by this time next year. So finally, I'd like to close by thanking the Almaris and Larson families for attending and their support for this lecture series. I'd also like to thank our speakers, Eric Davidson and John Jaski, for participating in this lecture series, and I look forward to their interesting presentations. And I will now turn it over to Al Levine, Vice President for Research, who will say a few words about the university and to welcome our guests as well. Thank you. Thanks, Bill.
Good afternoon, everyone. I'd also like to add my welcome to this. Today's a special day for this department. It's Mark Seeley's birthday. And according to my calendar, it's also Jay Bell's birthday, and I asked Mark, the two of them never co-celebrated, so maybe my calendar is wrong on that. We don't know for sure. So this university is the only research university in this state, and we are ranked in public universities 8th in terms of expenditures on research. We're close to $1 billion annually. So it's a very large university, and it's a very diverse university. There are very few that have agriculture, public health, law, medicine, public affairs. You can go across, we're very, very comprehensive. And I learned that when I got here. I came here to do my graduate work in wetland ecology with Evel Gorman. There was so much available that I must have changed my major 7 times until I got my PhD in nutritional biochemistry. So this university's diversity offers our students the opportunity to switch and do things. The last time I thought about soils in a deep way, I took a course with Ed Schmidt, soil microbiology, many years ago, and I worked on fecal homogenates, which has something to do with manure, human fecal homogenates, and I actually published a paper on carbon monoxide utilization in those microbes, but it turns out I went out and took soil samples, and guess what? Those same microorganisms and the same metabolic processes were present in the soil, maybe from animals. But that was an interesting area to work on. And I'd like to add my thanks, of course, to this great series, to the Ray Almaris family, and also to Bill's family, who I got to spend some time with Bill Larson over the years and really enjoyed his presidents, and it was a sad day when he left us. Soil, water, and climate is a great department to support. We're glad that there are people out there supporting it. People talk about dirt all the time, but soil is a different organism. I can remember, and I won't tell you who it was in administration, thought, well, why do we have to worry about this land that we have over in Umore Park with the soil and all the work we've done over the years? We could just bring in new soil, not understanding that it's a living organism. So the diversity and the idiosyncratic soil and waterways we have in the state are very important. So we're very delighted that you're here today, and we thank our speaker, and welcome. Thanks so much.
Thank you very much, Alan. I'm Mark Seeley on the committee, and I too have personal ties to both the Almaris family and the Larson family. And so I'm very grateful, even in retirement, to be associated with this program. We have two more speakers before our keynote speaker today, and the next person I'd like to introduce, and we're privileged this year because we don't always get our Dean present with us for these functions, but Dean Brian Burr is going to address us for a few minutes. And those of you not familiar with Dean Burr, he's been on the faculty here since 1992. He's been our Dean since 2013, I believe. Before that, head of the Department of Applied Economics. And so we'll hear from Dean Brian Burr for a few minutes. Thanks very much. Let's welcome Dean Burr.
For the introduction. Appreciate the brevity of it. I also noted when Satish was introducing Dr. Seeley retiring soon that you noticed that he forgot whether Dr. Seeley had retired or not. And it occurred to me that either means that you weren't doing enough when you were here or you're doing too much now. I'm not sure which is the better, but we're certainly happy that Mark still joined us on Friday mornings at 6:55 in the morning with Kathy Werzer to give us the weather. And I'm sure if you weren't there, commuters would just be crashing all over Minnesota, not knowing what to do about the weather that day. So it's great to have that. Satish, I want to thank you also for organizing and hosting this for several years, the work you've done, certainly. I didn't realize I was sort of, Carl just dropped the bomb on me he was referring to about you, so certainly that will be another place where you'll be missed in the work you do. I do want to thank the Larson-Almaris families for coming today. It's great to see everyone. It's been a little bit, as Mark said, I was at one of these sometime earlier, and appreciate you all coming and supporting this lecture and the contributions you made to that. I did, and then Mark also noted that my background, I was the head of applied economics, and I hadn't planned to talk about this, but before that, I was an animal scientist. So as an animal scientist, of course, I guess we're on the manure creating end of it. And decided I wasn't apparently creating enough manure. It just occurred to me because I became an economist, so you can spread manure far and wide, as most people would comment about the work we do. But it's more about the campus this year. It's a great time here to be on campus. And for those of you, not too many people talk about, we're talking about research today and the work in soil science and the implications of that, of course, on atmospheric sciences that would appear in the microbiomes of soils. But this is a time of year that's really a celebratory time of year on any campus because, of course, last week, if you were here, was our graduate commencement ceremony in the North Star Ballroom here on campus. And we do that so that our grad students can show their families around the campus and see the places, the fields, the greenhouses, the laboratories, where they've done their work over the last several years for their master's and PhD programs. That's a fun event. And then next Friday is our undergraduate commencement ceremony. So you're right in between those and the snowstorm is where you fit in here today. And we're delighted because over the last few years, and given, I think, the challenges that we face, and President Kater talks about the grand challenges of food, agriculture, water quality, Satish, you're all in their soil, of course, health and fertility is a big issue. And we're seeing our enrollments of students in CFAMs grow fairly consistently in areas because recognizing that this is a place where not only you do that hard, deep science that's required to make these changes, but you also have the opportunity here to engage in real life activities related to solving some of those challenges and seeing some hands-on work. How do we improve water quality? How do we improve soil fertility? How do we manage the carbon exchange that's occurring between soils? And of course, with animals, we have the questions regarding nutrient management, whether that's commercial fertilizers or manure, and where that fits in. So today's lecture kind of ties into that. And Carl took a little bit of my thunder on the things that we do here, but still he didn't quite hit them all, because I did think about how much, I'll just call it stuff, we do here related to manure, because he mentioned that several of these positions have been hired in soil, water, climate recently, focused around directly manure in some cases, but soil fertility, precision agriculture, and those are all parts of how do we produce and engage in more productive agriculture, feeding people while we're also conserving our natural resources. We actually just, we have a big data initiative here. It's called the Agroinformatics Alliance, and GEMS is another name for it. And it's a platform that we look at for computational sciences, and biology is really the platform for it. It cuts across a lot of the work we do. So one of our faculty members in plant pathology, Linda Kinkle, just recently had an NSF award to work on soil microbial plant interactions and plant health. That's a multi-million-dollar project. She's using that platform to do the big data work to try and understand the interactions with that. We also have a partnership as a result of that, the Soil Health Partnership, which is actually a national partnership with corn growers, looking at how do we in cropping systems improve soil health and fertility. And that, again, is a highly data-intensive system of how do we look at what's being grown, the interactions of the soil microbiome again, soil till, organic matters of soil, start to look at how that changes over time in a more controlled environment. The soil, one of the things, I almost always call him Dean Levine. He was vice president of research. He was the dean of the college immediately before me, and he had to mention Newmore Park, which makes us all very pleased at some level. But there's work going on there between the soil and atmospheric interactions that is occurring. Work with Tim Griffiths and Roger Becker and so on. They're working on those interactions. That's a huge part. As we're looking at climate adaptation, climate change issues, cropping systems, manure management is a big part of that. And I also have to mention, since we're more on Hall, we have an initiative called Forever Green. That's a major initiative looking at cropping systems, and whether it's cover crops and perennial crops, and how does that affect our ability to manage water quality issues. And certainly, again, that carbon issue in soils, and right now there's research going on not only to the development of those new crops, but looking at what are the ecosystem services and values related to those on the landscape. And then the other bridge is to food science nutrition. How do we bring those novel crops into consumable products for consumers? And so all through that thread boils down to our guest speaker, Dr. Davidson, who we're happy to have here today, to talk about some of those interactions between nutrients. I noticed, in fact, if you look way down, if you get tired of reading his long list of accomplishments, he was considering economics as part of that question of what's the interaction between manure as a fertilizer and what's happening with animal systems, and then bring economics into it. So I always have to get that plug in. We're a leading institution for ecosystem service valuation. Steve Plasky does work on how do we value those ecosystem values of cleaner water, more healthy soils, the wildlife, and other aspects of the externalities that come with cropping systems and perhaps livestock management. So a very comprehensive view of how appropriate and how interested I am in hearing Dr. Davidson tying all of that together into an hour lecture. I'll be looking at that piece, so we're just delighted that the Washington Mouse families host this to help us to bring a speaker like Dr. Davidson to campus. And it really does highlight a lot of the stuff we do here. I'll just use the word stuff as a substitute for the really good things we do here through the years to try to address these really challenging issues. So with that, thank you for coming today. Thank you for hosting, and thank you all of you for participating in this as well. And Dr. Cedar will have you come back, I believe.
Thanks very much, Brian. We really appreciate your presence here with us today. One of the unique and valued attributes of this lecture has always been we've had someone to share a Minnesota perspective on the topic. And this year, we're happy to have John Jaski, the Executive Director of the Minnesota Soil and Water and Soil Resources. John is a native of Minnesota, grew up on a dairy farm in Morrison County up in central Minnesota. He formerly was the Dakota County Water Resources Manager and Administrator of the Vermilion River Watershed. John has degrees from University of Minnesota as well as Minnesota State. And he's going to share some perspectives and thoughts regarding this soil health initiative with us today as a precursor to hearing from Dr. Davidson. So let's welcome John Jaski.
Thank you, Dr. Seeley. I do want to thank the families. That's a really important way you kept this going these years. And I just came from my family, which is, Dr. Seeley mentioned, up in central Minnesota. My mom's having some health problems, so I literally took off my boots this morning and had to put on a suit to come here and take a shower too, by the way. But our farm is still up there. My neighbors are the ones that now manage, and they do the cropping, and they of course got dairy cattle, and they have manure to deal with and all that. So it's not much different than it was when I was farm laborer number one. I have 10 younger siblings, so we all had to pitch in. But I want to speak to it from a practitioner perspective. University of Minnesota, you've heard Satish, by the way, congratulations. And you know, Satish, you can thank him for one thing right now. Last time when I got my PowerPoint sent to me from one of my staff because I was up at the farm, and he looked at it and he gave me a very polite, could you please, you know, cut it down a little bit? So I tore the thing in half and in half again. So thank you, Satish, for that. And you'll be thanking me as well, because actually Dr. Davidson and Dean Burr also covered some of the things that I was going to elaborate on. But I'm going to give you more of a commercial than a lecture, and that'll come next. So, and Carl, thanks for having me here today too. I appreciate it. So what my job is to work with local governments primarily, as well as our federal agency partners and private landowners. Our conservation programs in Minnesota are delivered locally. That's really, really important, whether they're through the government agencies, either federal or local or state, or whether they're delivered through the private sector, through the people who are consultants to ag producers and others who are managing their land, in most cases for production purposes, right? Because one of the things that this university has done, in my opinion, of course I graduated from here a long time ago, so I'm biased, but, and I was a geology and geophysics major, by the way, over on the other campus, but I had the good fortune, maybe good luck, to have taken electives just by random that you could take over on this campus. And every elective that I did take then ended up being a class over on this campus. I learned a lot more in terms of what I actually do these days, and probably changed my career from being an oilman to a conservation professional. And so I want to thank the university for that. They gave me some exposure to things that I probably didn't know about. And, you know, my dad, I wouldn't have made it to St. Paul, I don't think, because our farm was on Highway 10, and Highway 10 became, County Road 47 became University Avenue, and he had 4 hours to get me to school, in fact, before we had to go milk the cows. So we loaded the pickup. I drove down, I said, you're going back, the gas tank's full, don't turn, and you go right to Randall. He made it home. No cell phones or anything back then, so I called my mom, and she goes, yep, the pickup's here, he's home. So that was the last time he came to Minneapolis in terms of university, but we have a good memory of that. So and he's of course now passed on, so I wanted just to acknowledge his role in my time at the university. So, arrow buttons. A few things that are happening. I'm going to give a very, very high-level overview here, and we'll talk a little bit more about the University of Minnesota and all the things that it's done in terms of conservation, water, soil, and production. But one of the intersections of all those things that we're going to try and accelerate a bit is through an Office for Soil Health at the Water Resources Center, of course, supported by Extension. I know Dean Durgan's probably not here, but we want to make sure we acknowledge the Extension too. Another huge part of why this university has been so influential on Minnesotans, getting information that's generated by academia and research out into the hands of people who can actually use it, and that's such a critical part of the university's mission as well. We are looking at doing some science-based collection of information now using technology that once was, boots on the ground checking our fields and landscapes, and now we can do a lot of that with remote technology from satellites and so forth. Dean mentioned the intersection of conservation and production. and some of these innovative cropping systems that are being developed here at the university and elsewhere, trying to find ways to put those into practical terms for producers who could sell those to a market that allows them to make a reasonable profit. You mentioned a couple of them, and I'll maybe highlight a few more. We have local governments making plans for how they're going to manage things on a watershed basis. We've got, in this case, we got a North Fork Crow River watershed plan. Starts out in way western Minnesota, west central Minnesota, near Bruton and Belgrade, and goes all the way to just north of Minneapolis. That watershed is full of beautiful lakes, high-value farmland, lots of irrigation in some places, growing cities. The demands on that landscape are huge, and one of the things that this local organization, consisting of a number of counties and saltwater conservation districts and watershed districts, is doing is focusing on soil health as one of the ways that they're going to try and achieve all of those things over that very large landscape. Partnerships, I think there's more that obviously I'm never going to be able to list here, but the private sector's been big in this too. The corn growers have got a soil health initiative, and they're spending money from their members to do this kind of work and show people what is possible in Minnesota. It's not quite as easy as it is in other parts of the country because of our climate, and so we've got to make sure we have unique applications here in Minnesota. So what is soil health? I mean, most of you here are quite learned in this already, but this is a layperson description. We try and talk about this to people who understand, it's not just dirt anymore, right? It's a living organism that is going to, frankly, probably drive the future of our civilization in many ways. It's done that in the past, and I venture to say it will in the future. Think about the whole world and think about two things, fresh water and productive soil. And think about all the places on this planet where we got those two things in abundance. And there aren't many places that can do better than what Minnesota's got, right? Those two things together are probably going to drive the future of humanity. And so we need to make sure we're going to do a good job with both of them. The good news is that both of them are something that we can treat better and manage better and make better in terms of both production and other conservation benefits that go with that. But this is a layperson version of a definition that we use to talk about what soil health really is. Plants, water, and water moving through the soil, and plants growing and providing nutrients into the soil and taking nutrients out of the soil. How do we recognize this? Pictures are not easy to show of a soil, right? It doesn't move very much. It doesn't jump up and down. It doesn't go over a dam. It's hard to show what soil is really doing. It's slow processes. But it's these combination of things, of the air, the organics, the minerals, all of those things in combination, and the chemistry that ties it all together is really what drives what we would decide as be soil that's healthy. And you think about humans too, the comparison is not so big a reach. A healthy human looks like any old human, right? But when you see a human who isn't healthy, then you start to notice it. And so one of our biggest challenges is trying to get people to understand that it's more than just looking at it. And the good news is that in today's environment, we've got much more data, and the private sector has really led that. The crop consultants are helping landlords understand what's going on in their soil. Farmers knew these things intuitively, going back years and years, and still do. But today we're learning a lot more about it because we can collect data to help us understand how to apply materials that add to the soil or how to supplement it with natural characteristics. It's like I said, it's easy to see when we don't have it, right? It's one of those things you see a problem, you know that's not healthy, but when you see healthy soil, it's really hard to describe it. And these are anomalies, obviously, but this is a situation in both cases. No one wants this, right? This does nothing good for the public who's having to deal with these problems, and it does nothing good for the landowner who is trying to use that property to grow something. And so part of it is making sure people understand what the choices are. Every site's a little bit different. Soil types vary a great deal across Minnesota. landscapes and topography that we manage in the state also vary greatly. So my theme, my one single point I'm going to make today is that we have in Minnesota a lot of cropland, and it's very highly productive. We have terrific soils. We have water that is the envy of the world in many cases. And one of the things that we're going to be working on, and some are, of course, working on this already, is how to use this landscape to achieve managing water for water quality and for water volume purposes in a way that can also not compromise the production value. You know, a lot of this land has been altered already, you know, through drainage systems. Those systems allow us to do more in that soil as well, because we can now have a more assured cropping system in terms of getting in and out of the field, harvest as well. We can use that soil profile to hold water and treat water and get production benefits out of it at the same time. That's the, in my mind, that's the big opportunity in the decades ahead. So here's a few folks, just a list of those who are already obviously involved in this soil health enterprise. One thing I made my staff do, they put this slide together, is put farmers right at the top and put those agencies down at the bottom, because sometimes we tend to think of it as a you know, someone telling you what to do. But this is a situation where we need to have landowners, whether they're owners or renters, understand what's possible and what's in their long-term best interest. And so everything needs to aim at that producer. Obviously, some of these same principles apply to urban areas, managing turf and so forth, but the biggest opportunity and some of the biggest challenges lie with the agricultural land in Minnesota. We've got soil health teams at the local level, and some of those folks might even be in the room today. A number of organizations, nonprofits, and agencies doing this work. Of course, university, I just mentioned a few things. There's quite a few things going on. I didn't get them all, I'm sure. But one of the things that has been, I think, a critical part of this, as Dean Burr described, is how to use the principles of soil health to drive economic decision-making as well as environmental or conservation decision-making. I think that intersection is a sweet spot we need to be looking at. And this Office for Soil Health is really going to try and start at that point. And you can see it's a collaboration of several organizations already, at the university, as well as in state government, federal government, and local government. And we have a process underway to recruit and bring on board a soil health specialist here at the university. That's really important that it be associated with the university with a mission to drive decision-making and practices out on the land. And we're really excited about having whoever this will be. The person's not yet named or known or recruited, but when they're here, hopefully we'll get a chance to bring them back and talk to you more about some of the things that they have ideas on, and we'll be working with a group of Minnesotans to help guide their work as well. So with that, that's the end of my commercial. Thank you for your time, and we'll get on to the real part of this conversation, which is Dr. Davidson's lecture. Thank you.
Thank you, John. I don't know if you know that Bill Larson was the first person who coined the word soil quality and soil health. And it was in one of his science papers that published, I think, about 20 years ago or so. We think it's an important issue, and we surely appreciate your highlighting this issue for us over here. Stacy, do we need to do anything here on our featured speaker for this lecture is Dr. Eric Davidson. Dr. Davidson is a director and professor at the Appalachian Laboratory of the University of Maryland Center for Environmental Science in Frostburg, Maryland. Previously, he was a senior scientist and served a term as a president and executive director at the Woods Hole Research Center, Wood Hole, Massachusetts. His research is in biogeochemistry, includes the exchange of plant nutrients from the land to streams and groundwater, and the exchange of greenhouse gases between the soil and the atmosphere. Dr. Davidson holds a PhD in forestry from North Carolina State University and held a postdoctoral position in soil microbiology and biogeochemistry at the UC Berkeley and the NASA Ames Research Center. He's a fellow of the American Association for the Advancement of Science and president of the 60,000 member of the Scientific Society American Geophysical Union. If you know, Dr. Davidson has written a pretty popular book called You Cannot Beat GNP, and I have been reading that book, and it's a fascinating book. So if you get a chance, please read that book. The title of his lecture is Manure Happens, Unintended Consequences of Nourishing Over 7 billion Human Omnivores. Please welcome Dr. Davidson.
Okay, thank you very much. It's such an honor to be here. It's obvious that I'm in a very inclusive community that very much treasures the value of the participation of the families that made this possible. And since this is sort of a family event, I thought I might stray a little bit before I go into the talk and say something about my family. My parents were both born in Montana, and my dad had a job for a couple of years in Minneapolis, and that's when I showed up. And so this is sort of a homecoming for me. It's interesting to come here to see from whence I came. My parents moved away when I was still quite small, so I don't have any childhood memories of it. And my family is now spread out around Montana and Idaho and Washington State. And I have a cousin here who I'm going to take this advantage to visit while I'm here. So I'm really pleased to be with you. Since you mentioned you can't eat GDP, and since the dean is here and is an economist, I'll also stray there a little bit. That was, I had something in my craw back in the 1990s that I wanted to get out about the relationship between ecology and economics. I was motivated with that title partly by a very famous economist who at that time, as the climate change issue was gaining steam, said, well, I'm not really too worried about the effects of climate change on the economy, because the only sector of the economy that's really affected by climate is agriculture, and it only contributes 3% of the GDP. That doesn't quite make sense. I'm not suggesting that agriculture is going to crash, but if it did suffer, what would we eat? Could we eat the other 97% of the GDP? So, hence the name of that title. Well, I hope, as you can see, I like cute titles, and I hope this isn't the case of bait and switch with this title, because this is not manure management talk. Nobody's rushing to the doors. So that's largely a metaphor about the way that humans have changed, and are continuing to change our biosphere, and the way that we can find sustainable ways to continue to feed a growing population without a lot of unintended consequences. 7 billion, well, we're past 7 billion people. There are probably 300 million or so in India that are vegetarians, and maybe another 100 million in the rest of the world that are vegetarians. So given round off error, I'd say this is a pretty good estimate of how many people eat both meat and vegetable products. I'd like to back up and put this in perspective of understanding about nitrogen. How did humans come to understand what nitrogen is and what role it plays? And so I'm showing this in terms of a timeline of human population. I see at the moment that somehow the axis indicators are not here, but this is this axis should be human population in millions of people, so that's 7 billion people. Back before the Industrial Revolution, there were less than 1 billion people on the planet. And it was about that time that chemists working in the 18th century, started putting together the periodic table, understanding the different elements and how they relate to each other. And so nitrogen, it wasn't like nitrogen was invented then, but it was recognized as an element on the periodic table at that time. And then in the early 19th century, it was recognized that nitrogen is necessary as a nutrient for all of life. All plants, animals, microorganisms require this as an essential part for life. It makes up the amino acids that we have to make enzymes, to carry out all the physiology, among other things that nitrogen does for us. Then in the late 19th century, it was discovered that there are certain organisms that are able to take nitrogen out of the air. This 80% of the air we breathe is dinitrogen gas. It's harmless, we breathe it in and out, it doesn't have any impact on us, but it's not available for organisms to use for that essential nutrient capacity because it's a molecule that has two nitrogen atoms joined together by a triple bond, and it's very tightly bound triple bond. And most organisms can't use it. But there are a few organisms, largely such as the rhizobium organisms that are in nodules of leguminous plants, for example, such as soybeans. There are some blue-green algae is a common name for another kind of organism that has this, that have the capacity of taking that nitrogen out of the air and converting it into an organic form that supports life. And we call that biological nitrogen fixation. It was long about World War I that humans figured out how to do that through our technology. And it was driven largely by concerns over munitions, availability of munitions in World War I. The British controlled the seas, but the source of nitrogen used for munitions mostly came from Chile. And the Germans were very worried that they would not have access to adequate sources of nitrogen for munitions. The N in TNT is related to nitrogen. So they started an intensive program, an engineering and science and engineering program, carried out by Haber-Bosch. And they figured out how, under high pressure and high temperature, they could take nitrogen and hydrogen gas and make it form ammonia. And from ammonia, they could then transform it into other forms of nitrogen that could be used for munitions. So this largely came from that source. It wasn't until World War II, or after World War II, that this started to be used in a significant way to make fertilizers. And so this trajectory is the Haber-Bosch process. And so my units are down here, teragrams of nitrogen. What the heck is a teragram? It's 10 to the 12th grams. Does that mean anything to you? It's a lot. And you can see that we weren't using hardly any prior to World War II, even though the process had been invented in World War I. It was really after World War II that this crescendo enabling this growth of the human population. Estimates are that more than half of our population is dependent upon this source of nitrogen. So if we take 100 units of fertilizer, and whether you call it pounds per acre or kilograms per hectare, or whatever units we want, let's just say 100 units of fertilizer, and we put it on a field, how much do we consume? Well, this is kind of a rule of thumb. It obviously depends on the crop, and so I hope you don't hold me accountable for the exact numbers here, but this is a general average. It's a rule of thumb, that there's some loss even before it gets onto the field, and then the crop only takes up on average about half. Some of this will stay in the soil, some of it will be lost. And then what's harvested is not everything in the crop is harvested. Some of it is other material that is not part of the harvest. And then as that gets processed and going into some sort of food, even a smaller fraction goes into the food, and then we have food wastage. And so what really is consumed of that 100 units might only be about 14. And that's if you're a vegetarian. If you're eating animal products, we have a similar process here, but there are a couple more steps. And that the crop is now being fed, now going to animal feed, and that goes to the livestock. In the process, the livestock, this is where the manure happens part, and then we consume some fraction of the livestock. So in this case, only about 4 in 100 units are actually going into the feed. So it's an inherently leaky system, isn't it? If we think of it as flowing in through a pipe, on one end we're putting in our synthetic fertilizers, our manure, our natural nitrogen fixation, and let's go through the crop production pipe as a metaphor. And there are holes in that pipe out of which different forms of nitrogen leak. There are gaseous forms such as ammonia, nitrous oxide, nitric oxide, and this dinitrogen gas that is harmless. And there are soluble forms of ammonia, and nitrate, dissolved organic nitrogen, and there are particulates that are carried away in surface waters. And then some of that crop production goes to human consumption, but most of it goes to animal consumption. And then once again, we have the same leaky pipe. What we try to do in improving the efficiency is to figure out ways to make some of these leaks smaller, so that more of what's going into one end of the pipe comes out the other end. And that's our objective, trying to improve nitrogen use efficiency. We will never have 100% efficient system, because no biological system is 100% efficient. There will always be some leakages. And so that's one of the conundrums of the fact that our population is growing. There will always be excess nitrogen somewhere as a result of that. But we can minimize the impacts. The smarter our agriculture is, the more we can minimize those impacts. So, the Haber-Bosch process of being able to produce nitrogen fertilizers is one of the greatest, probably the greatest health boom in human history. Well, maybe antibiotics might be up there along with that. But on average, we are better nourished than at any time in the history of human race. It's not evenly distributed. There are still about 800 million people on Earth that are malnourished, and there's about an equivalent amount that are overnourished, and obesity is becoming a tremendous problem. And so as we think of how we're dealing with these health problems, and also it's not just under or overnourishment of humans, the same thing happens with under or overnourishment of ecosystems. And so as a result of that overnourishment of ecosystems, too much nitrogen accidentally leaving the fields and going into our ecosystems in other ways, we end up with a bunch of unintended consequences. And I'll very quickly go through these. Eutrophication of estuaries, that means nutrient enrichment of estuaries. Dead zones, I'm sure you've all heard about the dead zone in the Gulf of Mexico. Harmful algal blooms, nitrate in drinking water, some air pollution, greenhouse gas, stratospheric ozone, and acid rain in that biodiversity loss. So I'll go through each of those. So we have an extremely efficient system. We no longer have a lot of people living in rural areas. They move to cities, they do other things, they come to universities like this. And we have a very efficient system that produces food that's very nourishing at an affordable cost for most of us in the world. But we have these unintended consequences. And if I had a sign like this in a cornfield, and and thanks to PowerPoint, we do. What I would want to put on it is another little slogan, that we need more food with low pollution. Mo-fo, low-po. It's really easy to remember, okay? That's what we have to do to feed our current 7 billion people, likely going to 10 billion people by the middle of this century. So how are we going to do that? Well, first of all, let's go through some of those unintended consequences very quickly. I'm sure you've all heard about the dead zone in the Gulf of Mexico, but that's only one of, each one of these pins refers to a place of hypoxia, in other words, low oxygen content, due to the runoff of nutrients that feed algal blooms. The algae grow and then they die, and as they decompose, that consumes the oxygen. And really, you can see that it's all across, of course, North America and Western Europe. The reason that there are fewer points across much of the rest of the area is really a reporting problem. There are probably many more areas than this. It's also growing, a very rapidly growing problem in China. Groundwater. This is a map from USGS from some years ago showing, I think it's since been updated, showing areas of the country where the shallow well water, which many people in rural areas depend upon for drinking water, the parts per million of nitrate in the drinking water. And the drinking water standard is 10. So there are a number of places in the country, where I come from now, in Maryland, certainly around the Midwest, Central Valley of California, Washington State as well, where there are surface wells that are contaminated with nitrate above the drinking water standard. And they estimated that there are roughly over 1 million people that are drinking water that's very close to the drinking water standard. Furthermore, although the deep water wells, the deep groundwater has a much lower concentration, it is gradually increasing. And there's a very long lag time between the time anything that we do on the surface shows up in the groundwater. So if this is increasing, it's showing what we've been doing over the last many decades. And it will, even if you turn that around, it will be many decades before it starts going the other way. So the reason the drinking water standard had been set at 10 ppm was something, a disease called the blue baby syndrome that was an important issue after World War II, where there were some children being fed formula that was made up of water that had high nitrate. And the nitrate in the human body prevents the blood from absorbing oxygen, and so these babies actually look blue. Well, epidemiology was in very early stages in those days, and they put a pretty big margin of error on top of that standard. And there's been some debate that maybe it should be loosened now, because basically for the most part, there are very few cases of blue baby syndrome anymore, thanks to enforcement of that rule in most cases. So even if there are places where people are drinking water that's a little bit over that standard, they're probably okay. But now there's more evidence, although the epidemiology is very difficult to do, of other effects of nitrate in drinking water, such as prenatal exposure, effects with neural tube defects, and part of the problem with this, however, is that, number one, we no longer know where people actually get their drinking water. A lot of people use bottled water, and so it's hard to do those sort of surveys and figure out exposures. And number two, there's a whole bunch of things that co-vary with the nitrate. So it's very difficult to prove cause and effect. So this is one source, birth defects of concern. Another is certain forms of cancer, particularly colon cancer. And the way it works is that, and an additional problem is we also get nitrate not only from our drinking water, we also get it from diet, nitrate and nitrite from such things as cured meats and green leafy vegetables. It's also in some of our medicines. But all of this is transformed to nitrite in the mouth, in reactions with saliva, goes to the gut, where it reacts with amines and amides, proteins in the gut, to form N-nitrosyl compounds in the stomach and in the colon. And that is made worse by the presence of if people that eat a lot of red meat. That seems to make it worse. People that consume a lot of vitamin C, that seems to ameliorate it to some extent. But again, the epidemiology is really difficult to do. And the conclusions of the World Health Organization is that ingested nitrate or nitrite under conditions that result in endogenous nitrosation is probably carcinogenic to humans. So you take that for what you want, what they mean by the word probably. But these have been shown to be potent carcinogens or teratogens in all animal systems, including non-human primates, in which they have been tested. Of course, they haven't been tested in humans for ethical reasons. Another source of nitrogen in the biosphere is not only agriculture, but industry and transportation sectors produce forms of nitrogen, particulate forms called PM2.5, that's particulate matter that is 2.5 microns in size, so we respire it deeply into our lungs. And also other forms of nitrogen help form ozone, which down here where we breathe is a pollutant. That's the bad form of ozone. There's a good form of ozone up in the stratosphere. And the epidemiology of this is much clearer. And the numbers are actually astounding, and yet most of us aren't aware of it. I think because we've never heard of Uncle Joe or Aunt Betty dying of PM2.5, right? They may have had respiratory disease, but there are multiple causes of respiratory diseases, including effects of smoking and so forth. But this is certainly a contributing factor. Another effect of too much nitrogen in the biosphere is changes in biodiversity. And I'll just give one example here from Southern California, where these areas have now been invaded by an invasive grass that burns. And the native grasses that used to be there never burned. These grasses grow more abundantly because of the extra nitrogen that's coming down in the rainfall. They produce a lot of flammable material. And so now ecosystems that were never exposed to fire before are being exposed to fire, completely transforming those sorts of ecosystems. And finally, I already mentioned the bad ozone. The good ozone is up in the stratosphere. It protects us from ultraviolet radiation. One of the best success stories of the 20th century was the Montreal Protocol that nations of the world came to agreement to reduce chlorofluorocarbons, which is what destroys this ozone layer. And our production of chlorofluorocarbons has come way down, although it stays in the atmosphere for a very long time. So actually, these Dobson units, or the impact of these elements on the ozone layer, the effect of the chlorofluorocarbons is still very large. But over time, by somewhere in the middle part of this century, the effect of nitrous oxide will be larger as it continues to grow, as we continue to use more fertilizers to feed people, whereas the chlorofluorocarbons effect will taper off over time. So N2O, which is a byproduct of our use of fertilizers, is the major source now, new source of ozone-destroying chemicals produced by humans. It's also a very, very important greenhouse gas contributing to climate change. So one of the things about nitrogen that makes it so difficult to deal with is that it has so many different forms, so many redox states, and it's in the air, it's in the soil, it's in the water, and it can move around from one place to another. So Jim Galloway coined the phrase the nitrogen cascade. that nitrogen moves from system to system in various different places, and each place it causes problems. And that cascade doesn't end until eventually it gets converted back somewhere in the diagram. I must have N2. I guess not. Eventually, one of these get converted back by denitrifying bacteria to harmless N2. But along the way, the same nitrogen same atom of nitrogen can have an effect while it's in the atmosphere, have another effect on algal blooms while it's in the water, have another effect on the stratosphere it goes in. So here's a very high-level summary of how humans have modified the nitrogen budget globally. So this thing, remember biological nitrogen fixation that was discovered in the 19th century. This is the natural fixation of nitrogen that was happening before humans invented fertilizers. There's a little bit that's fixed by lightning. There is a little bit that's fixed by combustion. So in the internal combustion engine, you also have high pressure at high temperatures. And so you fix a little bit of nitrogen there. There's also a little bit that comes out of coal and oil when it's burned. The big thing, though, is our introduction of fertilizer and our introduction of crops like soybeans, where we are facilitating more biological nitrogen fixation by planting alfalfa, peanuts, and soybeans. Of course, there's also biological nitrogen fixation that occurs in the ocean. But if you add all that up, the anthropogenic part, which is mostly from fertilizers, the anthropogenic part is about half of the total annual fixation. So we've doubled the amount of reactive nitrogen in the biosphere. So this is in units of teragrams. And when I talk to people about units of teragrams, if you talk about it too long, I sort of glaze over. And even though I gave you some slides on the implications of it, on drinking water and all those other things, still, because it affects so many different things, and it seems like it's somebody else's problem. Maybe it's the problem of EPA, maybe it's the problem of the agriculture, maybe it's the, so many different sectors are affected by it. One of the things that has really changed, one more point that I forgot that I was going to add here, is that of this input, about 80% of that nitrogen harvested from our crops goes to feed livestock. It's pretty incredible to me that you think about all those crops you see on the road as you drive by. We're only consuming a small fraction of that directly. The vast majority of it goes to feeding animals. So, back to what I was saying. Talking about teragrams of nitrogen often makes people's eyes glaze over. This figure came out a few years ago in Nature, in a paper that wasn't peer-reviewed, by the way. It was invited by the editors, in which the authors came up with this notion of a planetary boundary and a safe operating space for humanity. And it's not the greatest figure. You have to stand on the edge to read part of it, right? They've since updated it, and it's a better figure. But I wanted to show this one, because this is one that really transformed the policy community, because they could identify with this notion of a safe operating space. Now, from a scientific perspective, defining what that is and defining what this planetary boundary is that we dare not exceed in quantitative ways is difficult. And frankly, some of the numbers are kind of mushy. But nevertheless, it's had a big impact on the policy arena, and especially for nitrogen, because a lot of people in the policy area knew about biodiversity loss, deforestation, extinction of species. A lot of people knew about climate change. What's this thing about nitrogen already exceeding the planetary boundary? So it brought more attention to this topic than I think all of these sorts of lectures that I could have given, and many of my colleagues. In fact, some of the past lectures here, I noticed that Ken Kassman came and talked here many years ago, and he talks about these same sorts of things. But this is really has transformed the conversation. Now, not all the bad news is bad news. There's a lot of good news to talk about. If I back up and talk about this part, the deposition from combustion, we have the technology now to turn that down to almost zero. In fact, we are doing that in North America and Western Europe. It's still a very big problem in places like India and China. But as a result of enactment of the Clean Air Act and its amendments, particularly the amendments in 1990, signed into law by President Bush, the amount of nitrogen in rainfall has declined. These are data from my colleague Keith Eschliman, who's been doing these long-term studies since the 80s in Western Maryland. And the amount of nitrogen has declined over time, and the amount of nitrate concentration in the stream water has declined along with it. In fact, Keith has calculated that he believes that this effect of reduced emissions and therefore reduced deposition and reduced nitrogen in our streams has done more to reduce loads of nitrogen to the Chesapeake Bay than has the adoption of best management practices in agriculture. It's not that those best management practices aren't important, and they will eventually have some impact, probably but there's a long lag phase because it has to move through the groundwater first. Whereas this change in deposition from the atmosphere has had a very rapid effect on loading of nitrogen to the major rivers like the Potomac and to the Chesapeake. Another good news story comes from Nebraska, many of you may know Richard Ferguson, where back in the 80s, it was recognized that they had a groundwater problem of excess nitrate in the Platte River. And the legislature at the time passed a law of establishing groundwater management areas. So there were local jurisdictions, local governance that engaged local farmers to come up with schemes based on sort of stratifying the area based on how much nitrate was in the groundwater, also whether it was sandy soils or clayey soils, and depending on where the farmer fit in that matrix, they had to do, perhaps only had to do soil testing. In the most severe cases, they could no longer do fall application of fertilizers. And as a result of that, it's been a long time coming, but they've shown that groundwater nitrate has declined over that period, and excess residual nitrate in the soil has declined. This blip here, I believe, was a drought. It's important to have long-term data. If you stopped your data right there, you can conclude that there was no effect. Another important thing to note, however, and this is a good trick for the graduate students if you want to make your correlation look better than it really is, don't start at zero. I don't really recommend that, but you can see that the decline, although it is very statistically significant, has gone from 19 ppm down to 16 ppm, and the drinking water standard is 10 ppm, and I'll have to go about here to get to there, right? And this is a relatively shallow aquifer, so the change was probably more rapid here than it would be in the other places. So it's a tough problem, but at least we've got a good news story where things are going in the right direction. So Richard says we need to move on to something else. Just doing that, which they were able to do in the 80s, isn't enough. And so he's now working on high-tech precision agriculture, where using a machine that can sense the amount of nitrogen that's in the leaves through the spectral reflection, and then determine the amount that should be applied accordingly. And in doing so, comparing that with what the grower would do based on state recommendations versus this sense program, he can show that they can cut the amount of fertilizer by about a quarter, not really affect the yield, and this is partial factor of productivity and a measure of nitrogen use efficiency that went up considerably. And this is on-farm research. This isn't an experiment station. But let's not forget that not all of the world can do that. That's high-tech agriculture in Nebraska. My colleagues, Cheryl Palm and Pedro Sanchez, who've been at Columbia, they since moved to Florida, have done a lot of work in Africa, where sub-Saharan Africa, the average farmer can't afford any nitrogen fertilizer. It's either not available, or if it is available, it's unaffordable. And they get yields of about 1 ton per hectare, whereas probably in Nebraska, they're getting more than 10. By simply increasing the availability of nitrogen from 0 to up to 50 kilograms per hectare, which would be about 50 pounds per acre as well, they could triple that maize production, but it requires some sort of subsidy, some sort of effort to get the fertilizer and the right mix of fertilizer, not just any old fertilizer, it has to be balanced fertilizer, appropriate for these soils, can have a tremendous impact on food security there. And it has some additional benefit in that it improves water use efficiency, which is very important for rain-fed agriculture in eastern and southern Africa, where there are significant interannual variations in precipitation. Now, the question is, and I've heard this in many NGOs have said, oh, but we don't want Africa to make all the same mistakes that Europe and North America made. We don't want them using chemical fertilizers. It's true that if we add increase fertilizer use, 50, 75, 100, and so on, these are measurements of nitrous oxide, that, yes, indeed, you can increase nitrous oxide emissions considerably. But this example that they gave is only going up to 50. And as I said, there's never going to be a system that doesn't have any leaks. There's always going to be some leaks. But this research has shown that they can actually manage this pretty well and having pretty minimal additions, increases in nitrous oxide emissions. And they've done similar work for nitrate leaching as well. I suspect many of you are familiar with this, the 4 R's. This is a slide I borrowed from Paul Fixon from the International Plant Nutrition Institute. And the point I want to make here is I'm sure you're familiar with this notion of the right source, right rate, right time, right place. But the fertilizer industry is putting this now in a perspective of environmental, economic, and social consequences. And I think that's the way we all need to be thinking about it. And the fertilizer industry, at least IPME, is on board with that notion. I think I won't go through these. I've assumed that you know some of the agricultural practices that can be used for each of those. I present this for more general audiences. But now I want to talk about some international trends in nitrogen use efficiency. This is sort of the same hole in the pipe model that I showed you once before, where we have fertilizer, biological nitrogen fixation, manure, and deposition coming into our pipe, and crops coming out the other side. And we have leaks, either as dissolved form in water or gases coming off. And I'm going to use a different definition of nitrogen use efficiency now, where we say that the efficiency is simply the amount of nitrogen in the crops divided by all the inputs added together. Okay? So the maximum would be 1. The value, this fraction would be a value of 1, unless we're mining soil nitrogen, that would be more than 1. And another term is N surplus, which is simply the inputs minus the outputs, and that's what's left over that may be leaking out of the system. And if we rearrange that equation, we can put all of those into one equation, which allows me to now show the next graph, which is sort of a pièce de résistance of that. If we look at trends of different countries representative of the world, and on the x-axis have yield, so we kind of want yield to be going up over time, right? To make better land use efficiency, to feed more people. We want nitrogen use efficiency to be going up as well, and that's on this axis. And then the shading is the nitrogen pollution, or the N surplus. Each one of these dots represents a 5-year interval from 1961 to 66 to 71 and so on. So let's look and see what happened. The United States, which is in light blue, after World War II, we were putting on more and more fertilizer, and that helped us make more and more yield. Our yield was going up. But because we weren't using that fertilizer very efficiently, efficiency was going down as we put on more fertilizer, and we were going in this direction towards more pollution. But then things turned around, and they're starting to go the other way because we've started to use best management practices that make more efficient use. And we have better cultivars. That's probably equally or maybe even more important in terms of being able to use that efficiently. France did something similar. In fact, they turned it around even more because they got rid of a bunch of subsidies. And also Europe in general is more regulatory. Most of this progress in the US has been driven by technology and the marketplace and voluntary adoption of those things. But look at some of these other trends. Look at what China's doing. It's following the same path of using more and more fertilizer, which is increasing crop yield, but still decreasing efficiency. And they're going down into this dark, deep, dark abyss of nitrogen pollution. And they have one hell of a problem there. It's starting, there's evidence that since 2011, it started to flatten out and maybe turning the corner a little bit. The agronomists there know what is important. But the policy people are concerned about food security, and food security. Okay? Some other interesting trends. Brazil has kind of cut across. Sub-Saharan Africa, example of Malawi, they were mining nitrogen out of soil, removing more than they were putting back in. They've started to increase a little bit their yield, and as a result, their efficiency has gone down. The question really is, where is that going to go? We would like that to move this way before it has to keep going down that way. Can we figure out a way to skip that, the same way that some of these developing countries skip the landline telephone? They're going straight to cell phones, right? Can we figure out a way in these countries of skipping this period in which our efficiency is going down and pollution is going down? Well, our target to meet at least one estimate of food demand from the Food and Agriculture Organization, if all the world could have an average yield of just about 100 kilograms of nitrogen per hectare per year in the crops that they produce. We produce more than that in general here, but if that were the global average, and if on average the surplus never exceeded 40 kilograms per hectare per year, that would be sort of within that realm of planetary boundaries. Then what we would like is everybody producing up here. Higher yield, and actually the US and France are already in that area of yield. We haven't quite gotten up to that area of efficiency. And all these other countries need to turn the corner and go up there as well in order to get to that goal of adequate food production with less pollution. Mo-fo-mo-po. Well, N surplus is a form of pollution. It's a form of environmental degradation, and there's been some theory about that. In the ecological economic literature, the notion is that as a country goes through development and our per capita income goes up as we're first developing, industrializing, developing our agricultural sector, most societies are so concerned about income that they do so at the expense of the environment. Deforestation, development of industry without pollution controls. They get to a point on this so-called environmental Kuznets curve where they have enough wealth and they have enough well-being, and they start thinking about the value of the environment around them. That they also want clean air and clean water, and they also have access to education and technology, so they can do something about this. And so the theory is that at some point you reach a turning point in this environmental degradation. And we wondered, would the same be true if we applied that to agriculture? Nobody else looked at that in terms of agriculture. And we found that for every country that we looked at, almost every country we looked at, and France and the US are two of the best examples, that yes, that seems to be the case. That as our GDP per capita increased, and each of these dots is a year from 1961 onward to the present, as our per capita GDP increased, surplus first went up and then it came back down. Although the inflection points are very different because our societies are very different, our economies are different, and our regulatory approaches are different. So there's no magical GDP number where this happens. But all of the major countries of the world that we analyzed at least are showing some flattening out of the curve. So again, there's some other reason to have some good news and hope. It's a difficult problem, but we're moving in that direction. So what are some of the things that factor in? Well, one of them is economics. This is a graph of the ratio of fertilizer to crop price ratio. So the more expensive the fertilizer is relative to the value of the crop, the more incentive the farmer has to use that fertilizer wisely. Well, China, over this period, that price dropped because of subsidies for the fertilizer. And China is one of those that has not yet turned to corner. Whereas for the US and France, the ratio of fertilizer to crop price has increased, and farmers are making more efficient use of their fertilizers. But economics isn't all of it. There's a big part of it that's sociology as well. This is a study from Linda McCoppy at Purdue University. I presume it was done in Indiana, and I'll be very interested to see if you all feel that these results are consistent with what you know about Minnesota. She found in asking farmers where are their most trusted sources of information, most of them said family. So the strong influence is up here, these two colors. Most of them said other family members, or where they buy their fertilizers from, or where they buy their seeds from, or their private consultant. Those are their trusted sources of information. And I'm sorry to say that University Extension kind of falls down the road here. It's even below bankers and lawyers. So another model now is that University Extension, which over the last several decades has, in many states anyway, has suffered from funding shortages, that in many cases their efforts are helping to have certification programs and professional training for these consultants, including the consultants that work for the seed companies and the chemical companies. And associations like the Agronomy Society of America, Soil Science Society of America, is focusing on accreditation for these. So it's sort of like you and I have an auto mechanic that we trust isn't going to sell us a brake job that we don't need. And these farmers have consultants that they trust. And it's not just coming up with a better management practice, a better type of fertilizer, a urease inhibitor, or better market signals. It's also a matter of how do you get the information out through trusted sources. So this is where the sociology comes in with the natural science and the economics as well. And now if we look to the global scale, the nations of the world came together a couple of years ago and agreed to the Sustainable Development Goals. Sustainable Development Goal number 2 is zero hunger, achieve food security and improve nutrition, and promote sustainable agriculture. Well, how are they going to measure that? What is sustainable agriculture? Well, the only thing they could agree upon was for each country to decide as their indicator the percentage of agriculture area under sustainable agriculture practices. That seems like kind of a tautology to me. And they're leaving each country up to define just arbitrarily what is sustainable. Are there ways that we can actually quantify it? And I don't necessarily mean at the farm gate. I mean at the national level. Can countries quantify the trajectory that they're going on for sustainability? So this is work with Xin Chang, a colleague of mine who also worked on some of that environmental Kuznets curve work. We're trying to come up with some quantitative indicators, looking at not only at these things like nitrogen and yield and so forth that agronomists and biogeochemists and ecologists look at, but also some of these societal factors and some of the economic factors. And just quickly, our goal is of this sustainable agriculture matrix, is to provide consistent and transparent measurements of country performances, to try to integrate these socioeconomic and ecological drivers, and to quantify them and put them in a visual way, sort of like that safe operating space for humanity. It's important how you visualize it to try to do this. So we have a lot of work to do. We're just getting started. But here's an example of just a few of the indicators we're using. And the colors here show the trajectory over time for the United States of land use efficiency. Well, land use efficiency is just another word for yield. And you can see that our yields have been going up. But if we put all of those together and then compare, we can use this for an individual country to see its own trends for each of these indicators over time, or you can compare countries among countries. And here I only have a dozen of these. We're now up to about 30 that we're trying to vet to make sure that the data sources are reliable data sources, and whether the information is really useful information. Just because their data available doesn't necessarily mean it's useful. It's hard to find data that are available for all the countries of the world and that are reliable. That's what we're trying to work on. It includes such health things as obesity and prevalence of undernourishment. Or you can take a single crop and you can say, well, how does this crop compare if it's grown in different countries? So for maize, for instance, we have a bit of a problem with groundwater depletion. China has a much bigger problem with groundwater depletion. Oh, by the way, I forgot to mention, I'm sorry. Being closer to the center is bad. Being closer to the circumference is good. I should have said that at the beginning. And these are all normalized globally. So I don't want to belabor this, but this is an approach we're trying to take to come up with some quantitative indicators of sustainable agriculture. And finally, I want to get to our responsibility as individuals. I've talked a lot about what governments do, what farmers do, what agronomists do. Of course, many of you are agronomists or farmers. But I also want to talk about what each of us does as consumers. These are projections about consumption of animal protein from some studies a ways back, early about 2011. And you could see that the projections of increased animal consumption, particularly in countries like India and China. But even if you put it on a per capita basis, they were projecting that even in the United States, which is already consuming a lot of animal products per person, that will continue to grow. But a funny thing happened along the way. Actually, our per capita consumption has started to decline. Now, I should note that this line that shows declining beef consumption and increasing poultry consumption comes from the National Chicken Count. So this could be fake news. Assuming that it's accurate, why has this happened? Well, I think it's a remarkable marketing effort and also a transition of technology that we can now grow chickens very efficiently, and they're very nutritious. You know, when I was a kid, chickens didn't have fingers, but now they do. Now, did this downturn happen because of the economic downturn, or it seems to have continued even beyond the economic downturn? I would say that 50 years ago, if I were giving this talk in this room, I bet you half of you would have cigarettes today. And none of you are smoking here today, and it's not allowed, and probably isn't even allowed in the parking lot for years. People's habits do change. And this is, I think, a more difficult habit to change than smoking. And it doesn't mean that we have to all become vegetarians either. It has to do with portion sizes and frequency. You can actually now look up your nitrogen footprint if you want, thanks to the work of an ambitious graduate student. And just like you probably heard about carbon footprints, you can do the same thing for your own nitrogen footprint. In most cases, the majority of your footprint is going to be related to your food consumption, but they try to put in other habits in there as well. And they've done this for a number of different countries. They've done it for Tanzania, for example, and the Netherlands. This is an example of carbon footprint, but nitrogen footprint is pretty much the same. And I don't mean to suggest that we should all try to survive on oils, sweets, and condiments. Don't get invited back when I suggest that. But the point here is that each of us makes dietary choices. I'm not suggesting we all give up all red meat, but considering the frequency and portion size does make a difference in terms of the overall impact that each of us has. And that issue actually came up talking to students today about whether our personal choices add up and make a difference. And ultimately, all these markets are responding to us. We are voting every time we go to the grocery store. And so I like to lead with that notion that while there are many things happening in agricultural policy at the national level, at the global level, at the farm gate, in our research institutions, there are also decisions that each one of us makes every day that makes a difference. So I'd like to leave you with the notion that sustainable intensification of our agriculture can increase our crop yields. That's what we've been doing in this country lately. And it can reduce pollution. We've actually shown trends of reducing nitrogen surplus and increasing nitrogen use efficiency. These new technological advances will be very helpful, but there's also a lot we can do with existing technology. But in many cases, even the existing technology is not adopted because of those social and economic impediments that remain. So we have to integrate our agronomy, our natural sciences with the social sciences and other disciplines to get cooperation across sectors and stakeholder groups in order to achieve that mode forward, mode goal. Something like a sustainable agricultural matrix can help nations gauge their progress towards that sustainability and modify their policies accordingly. It's still something that we're working on in terms of research and trying to develop whether such a thing can be useful. And finally, our personal dietary choices do matter. So thank you very much for your attention today.
Thank you very much. That was a we're going to open it up for questions and answers. answer over here also for John. Any questions for Eric or John?
I have a question.
Sure.
You mentioned that in Africa, the fact was that wind wasn't used because it was unaffordable, I think is the word you described. You also described some technologies that the United States and other countries are able to have available, the slow release, things like that. Is affordability an issue with those?
Oh, yeah, they don't exist at all. I mean, even just getting, well, I shouldn't say more, I mean, that may be an exaggeration, but there are certainly some, there's certainly some agricultural activities that have the capital to go into that, so, tea production and something like that. But for the most part, the subsistence farmer who's farming a couple of hectares at most, doesn't have the ability to consider those things. They use manure, but their manure is a very low quality because their animals are malnourished as well. And even where they use the manure, they don't necessarily have the information how to use it.
Any other questions?
On the plot with the, I can't remember the EKC curve.
Environmental goodness.
On the French ones, it reaches a certain point, it goes like straight down for the last 7-8 years. Was there a specific legislation or trigger that caused that?
Yeah, so they did away with a bunch of agricultural subsidies in the 80s and 90s, and the nitrates initiative was adopted in the 90s, and it's been tightening over time in terms of restrictions on how much fertilizer farmers can use.
Okay. Thanks.
Yes.
Consider a portion of our corn use here in the United States actually goes to ethanol for fuel production. Is that manufactured in as well?
Yeah, we've looked at, in terms of the national average for the U.S., we include the corn that goes to ethanol production as an output, and that's part of the calculation of the trend in nitrogen use efficiency.
Any question for John? Any more questions?
I just have a question back for our main speaker. It seems like there should be some kind of disruptive technologies that are out there to really get us to jump from the sort of smooth lines we've been on to something that's a bit more sustainable. Here in Minnesota, for example, we're seeing a great amount of interest in growing perennial food crops, which have the ability to, the yields are much lower, but the nitrogen losses are much less as well. Have you ever considered something like that as a sort of pathway to get to less leakiness?
Sure. Of course, that would reduce your land use efficiency because you're reducing your yield. And we still have to deal with producing enough calories and protein. But if that can be done in certain areas, that would certainly be an approach worth doing. There's increasing trend towards fertigation in some places, and there's going to be more irrigation with climate change, and that offers an opportunity for fertigation would greatly improve nitrogen use efficiency. There may be, we've been dreaming about trying to get nitrogen fixation into grains. Maybe we'll end up someday producing the equivalent of animal protein without an animal. That would be a disruptive technology for sure.
Eric, I got a question for you. I've been reading part of your book too, and it kind of relates to that. We talk about we are improving our environment through the technologies, and we done so. And if you look back and you see Cleveland area and Ohio area is very clean, the river does not on fire. But most of our pollution, we are really exporting. We are exporting to China, we are exporting to India, and we're really getting benefit of that pollution without paying any environmental cost. So recently the question came that President Trump was going to put a tariff on China, and China said we'll put a tariff on soybeans, and the future for soybean in Brazil went up. And we're going to start cutting down the jungle over there and start growing soybeans. So what is the impact of these kind of issues when you look at, in terms of, we say we start growing maybe the, crops over here which are perennial, and they would cut down this, and we're still going to grow soybeans and go to Brazil and cut down Amazon.
Well, one of the potential values of this sort of sustainable agriculture matrix is that it would enable us to look at which countries do best for which crop. So that's sort of one of the underlying themes of assumptions of globalization is that you don't do everything everywhere. You do things where it's optimal. And so, for instance, growing soybeans in China is a lousy idea. There are a number of reasons that they just can't do it as efficiently as either Brazil or the United States. And you could do that, look at that crop by crop. Much of the reason that China nitrogen use efficiency is lower than the United States is that they don't have much in the way of soybeans. And they have a lot of fruits and vegetables. And they export a lot of their fruits and vegetables to Southeast Asia and Australia. So it isn't just that we're exporting our pollution to China. China is also involved in trade with other countries as well. These analyses that I did on a per hectare basis don't show that we're improving our ability on a per hectare basis because of our technology and know-how. And that is not affected by exporting. If you were to do a national accounting and saying, oh, we have fewer greenhouse gases emitted from, well, UK has done this. UK says, oh, we have fewer greenhouse gases emitted from our agriculture. Well, they're growing less food. So they're importing their food, and so what they're importing has essentially virtual greenhouse gases embedded in it. And so that's kind of cheating. And your point's well taken there. But the answer to that is, well, where are they importing from? And why aren't we transferring technology to those countries so that they can grow those crops more efficiently? And why can't we transfer what we've learned so that can happen in those places as well? And I don't think there's any reason that it can't happen.
Any other question? Last minute? If not, I'm going to have a black presentation, and then we'll go to the foyer and have some refreshment. John, you want to come over here, please? We have of the organizing committee. This is a token of our appreciation for participation. Thank you, John, and here is your flag. So what we're going to do is let's give a big hand to both the speakers.